couple of years ago, I was working at a small startup, and our code base was written in Scala, and there were so many issues with it that we decided to completely overhaul our architecture. But we were going to do it right. We were going to be functional. We added Scala Z. We added the state monad. It was going to be beautiful until we started seeing Stack Overflow errors. And this was just in testing. We hadn't even deployed this to production yet. So my coworker says, let's just trampoline it and add the free monad. And this was me being very confused what he meant. That was the first time I'd ever heard of the free monad. I had no idea what my coworker meant or why he intended it to solve our problems. And then fast forward a couple more years, I'm in a different Scala startup and a different Scala code base. And there was this one application that no one ever wanted to touch. And I looked at the code and I understood why. We were using free monads to do a very simplistic data store operation. The purpose of the application was really straightforward, but the code made it look really confusing, and that made small changes take a long time. Essentially, I wanted to know if I was justified in being annoyed with this application, so I decided to learn what the heck a free monad is so you don't have to. So today I'm going to talk to you about why the free monad isn't free. My name is Kelley Robinson. I'm an engineering team lead at an advertising company called ShareThrough in San Francisco. And let's get into it. So before we talk about why it's not free, we're going to talk about what a free monad is. And in order to do that, we are going to explain monads using monoids and functors. And then we're going to get into what it means to be free, why you might use some of these abstractions, and then maybe why you shouldn't. If you're not going to use them, what are the alternatives available to you? And finally, some of the applications people are using of this stuff in the real world. This presentation has a lot of code. Not everything on the slides is going to compile if you try to do that. So all the examples are on my GitHub. You can look at them there, and I just tweeted that link. All right, monads, monoids in the category of endofunctor. We have all heard this, but what does that mean? Oh, Bodo, did you want the picture? So let's start with monoids. I'm going to use these examples using Scala code. Quick poll, how many people don't know any Scala? Raise your hands. Fair, okay, like half the room. That's unfortunate, but we'll make this word anyway. So traits, similar to other object-oriented programming languages, you can extend them. The methods available to them will be available to anything that extends them. Type parameterization here means that this will take any type A method signatures, hopefully, are straightforward. The append method will take 2 parameters of type A and return a parameter of type A. So that is starting to sum up what monoids are. A monoid is just some type that is going to have a couple of methods defined on it. And it's going to have this append method that's going to take 2 of the type, and again, that can be any type, and return 1 of that type. And then some method, usually called identity, that's going to be a no-op or empty if used with the append method. So again, monoids, 2 of one type coming together to create 1 of its type. There are some properties or laws that apply to monoids. Like I said, there's this identity value that's going to be the no-op, and then the idea of associativity, which means that the grouping of the append method isn't going to matter, and that could be with parentheses or any other way. Buzz Lightyear is right, there are monoids everywhere. So we can look at a couple examples. String concatenation, really great example of a monoid. You've got the append method is putting 2 strings together. If you take 2 instances of a string and combine them, you're left with a single instance of a string. And the identity method there, the no-op value, is going to be the empty string. Another example of a monoid, integer addition. You can append 2 integers together and you're left with another integer, and then the identity value there, in order for it to have no effect, is set to 0. All right, let's move on to functors. A functor is going to be some family of types, some container that's going to have the map method applied to that. That F with the underscore next to it means that that's a container type. It's going to take something in its type. And the map method, as we might know, is going to be some method that will take a function and then apply that function to everything inside the container. So for those of you that don't know Scala, a visual representation, if you've got some container, that triangle that has some values inside of it, that takes a function, multiplying everything by 2. You get a new container returned that has all of the values that have been multiplied by 2. It's functors and pictures. Functors also have some properties. The identity value, that means that there's going to be some function that will have no effect if done with the map function. And then composition, like associativity, that's to say the grouping doesn't matter. So you can chain a bunch of map functions in a row, or you can put all of the logic inside a giant map function. All right, following me so far. Now we're on to monads. So I really like this quote from a Stack Overflow post that says the term monad is a bit vacuous if you're not a mathematician. An alternative term is computation builder. So this audience might have some academics or mathematicians in it, but for the rest of us, I think this is a really helpful mental model. So a monad is going to be another container type. It's going to be another family of types that's implemented the pure and the flat map methods. It's going to be this container, a context, some kind of collection. The pure method there is going to lift the value into that container, into the context. And then the flat map method, this is also bind for those of you familiar with Haskell, it's going to wrap, flat map will map all the values inside of the container and then flatten the context that that creates. So the interesting thing about this is now that we've defined the pure and flat map methods, we can kind of work backwards to define the functor and monoid operations. So here we've used pure and flat map to define map. And we kind of get this for free once you've defined the monad operations. And we can also use flat map to define the monoid operation of append. And I've been pretty explicit about how we've done this here, evaluating the functions in order to get to the next step so that we can flatten the context and return the result that we want as we're chaining and appending things together. Like the other two, monads have some properties. There's also going to be some no-op value. It's going to be a function that when used with the flat map method will have no effect. And then the composition to say the grouping doesn't matter. And again, you could chain a bunch of flat maps together or put it all together and it's going to be the same thing in order for it to be a monad. So revisiting our pictorial example, we have the context of the triangle, you map, and you get another triangle. But what happens if your map function creates another context? Then you're left with all of these nested triangles, and this is kind of unfortunate. And this is what monads bias. When you flat map, it flattens that context, and so you're only left with a single wrapper at the end. And this is a pretty arbitrary example, but monads are really useful because you can use them to compose values in a context. And in your programs, this is going to be things like lists and futures. At the end of your program execution, you want to be left with a future of a result, not a future of a future of a future of a future of a result. And that's why things like monads come up so often in programming languages. That was a pretty brief introduction, but now we're going to talk about what it means to be free. And before we get into that, we need to define what we mean by free. Let's clarify this. We mean free to be interpreted in any way. This means unrestricted, no interpretation. This is not about the cost of doing this. Or for the fans of Richard Stallman out there, free as in freedom and not free as in beer. So there it is already. The free monad isn't free, unless any of you want to buy me free beer later. So free monoids. Let's start with this to build up our understanding of free monads. Quick refresh, monoids, the append method, two of something coming together to create a single instance of its type. So what does it mean for a monoid to be free? Well, again, we want to keep it free from interpretation. Oh, am I stepping on something? And we can't lose any input data when we're calculating the result. So that's pretty vague, but we can look at some of the examples we talked about earlier in order to see what this means. So list concatenation is a good example of a free monoid, and that's because when you append two lists together, you're just shoving the data together. You're not losing anything about the inputs. And it's important here that we define this with the generic type A, because this can be done with anything. We don't know anything about the input, the contain type in the list. It could be ints, it could be strings, it could be functions or other complex types. But the fact that we don't know what it is means that the only operations we can do are the monoid operations that we've defined. And that keeps it free from interpretation, and that's why this is free. In contrast, if we think about something like an integer monoid, this isn't free because when we're combining two integers together, we lose information about the input. There's a special algebra that's happening here when we combine these two together, and it's an explicit interpretation for that type, and that's why this isn't free. So that brings us to free monads. So the important thing that we need to remember here is that we can't lose any data as we're flat mapping and chaining operations together. And that means we can't evaluate any of the functions. So if we think about the example we were looking at before, the result here on the right loses information. We don't know what the inputs were, we don't know what the function was, and that makes this not free. So how do we do this in a way that lets you evaluate this at a later point in time, that keeps this free from interpretation? So again, we're going to build up a syntax for how to do this. We'll start with some idea of a free, and then we'll add a class return that is going to indicate that there's no more computation, and this is going to be used in our pure functions. And then we'll add a class suspend, and this is going to lift the container, that f of something, into the context, and suspend it until we're ready to process that later. And then we'll add a class flatmap that's going to take an instance of free and a function from A to another instance of free. This is going to look familiar to the flatmap's method signature, the bind method signature, and that's going to help us out. Finally, we'll add some helper functions on the trait that will help us chain the operations together, and this helps with some of the Scala syntactic sugar that we need. So let's look at an example of how we would actually build this out. So let's define a free monad for actions on a to-do list, basically the most basic program you can write as a programmer, except for Hello World. So we'll add some syntax for the to-do list actions, things like creating a task, completing a task, and then we'll add some operations that will lift that into the syntax with suspend. But again, we're not doing anything right now. We're just talking about what we want to do, and we don't know what this means to actually create a task or complete a task. And that's why it makes it free, is because we haven't defined the interpretation. So let's see what this looks like. So in Scala, this is pretty cool. You can chain these operations together using a for comprehension. And this is syntactic sugar for flat mapping. And you can chain all of this together to get the result. And this might look familiar to some of the Scala programs that you might have seen, but again, nothing has happened yet. So we can look at the resulting data structure here, and this is what it's going to look like. And we've expanded it explicitly into its types. You can see how we're creating this list-like structure that chains all of these operations together with all of the inputs and the functions and how they've been chained. But again, nothing has happened yet. There's no operations defined, and that's why this is free. If we think back to what we had before, the result didn't have any information in it. What this might look like with the free version is something like this. We take the input data and also the functions that we're applying, and previously we think of this as the star value being some kind of multiplication, but again, that's an explicit interpretation for that operator. Here we've said, okay, 1 star 2, but we could later define that to mean whatever we want. And that's part of the reason that this is free. All right, so why would anyone do this? It seems pretty complicated. There are a few reasons. First of all, when you're deferring the interpretation, you're also deferring all of the side effects. You're composing functions without actually computing them, which means that you can delay and defer all of the side effects, all of the I/O, all of the errors until a later point in time. And then that syntax tree that we defined, that to-do list operator, the complete task, create task, we can use that syntax to later define multiple interpreters, like I was talking about with the star operator. It's like if I created a list of something and handed it to everybody in this room, you would all probably interpret that a little differently. And then you can think about something like this and use your imagination for what these do something functions do. They could be doing some kind of I/O, or they could be adding another 1,000 function calls to the stack. But in the course of your programs, things are going to start to look like this. Every function in the monadic context is going to be added to the stack. So remember my coworker? Let's just trampoline it and add the free monad. So when we talk about trampolining, we talk about wanting to express all of the control flow, all of the function passing, all of the chained functions in a loop instead of putting additional functions on the stack. All right, where is this? Any help? I just don't think it likes it. It thinks it's connected.
It's sometimes connected. Starting to think that adapter is broken. Yeah. Oh, almost.
I have a different dongle I can try. We'll try turning it off and turning it on again. Okay. Ooh, I think the dongle's broken. All right, so trampolining, we want to loop things. We don't want to put additional functions on the stack. So the free monad is what this is about. The free monad is going to use trampolining to achieve its goals of achieving stack safety. It's going to exchange stack for heap. Trampolining and the free monad all come down to exchanging stack for heap. So if you think about our not free example, you're going to be building up some kind of stack, putting additional function calls on the stack. But in the free example, we built up that data structure where all of the information is contained, and so your result is going to be just bigger. All of that info contained within that data structure that we created, expanded here. So we created this list-like syntax, and what are we going to do with this? How are we going to actually evaluate this? Well, we want to utilize trampolining. We want to use a loop. So let's talk about what this would look like. It's a little crazy, but the important things to get here is that you're going to have a generic function that you can run using multiple interpreters that will take your input. So it's going to take some kind of free input, the monad that you want to evaluate, and then some kind of transformer that's going to take that and transform it into whatever output type that you want to use. And there's also this implicit condition that the transformed type has to be a monad, and I'll get into that in a little bit. So the functor transformer is a little tricky. You might also hear this called a natural transformation. I wanted to be more explicit, and so I named it what it is, turning one functor into another. And we'll look at examples of how these interpreters actually work in a little bit. But first, let's look at the method body. This is already a ton of code, so I cut a lot of it out. But in pieces, the important parts to recognize are the tail recursion. In Scala, this is going to utilize the trampolining. This is going to avoid putting additional function calls on the stack. This is going to turn it into a loop. And then it's going to pattern match on those return, suspend, and flat map cases in order to do the evaluation. And I do want to highlight what happens on the suspend cases. This is where the transformation happens. Remember, the suspend is going to lift some kind of functor, some kind of context, until we're ready to evaluate. And that's what's going to happen now. In the evaluation context, we're going to take the transformer, the interpreter that we defined, and apply it at this point. One point that I wanted to make is you can do this even more explicitly. This might look a little weird using a while loop in a functional language, but this is what's happening under the hood. And I just wanted to illustrate that this is very possible. The logic here is exactly the same as using the tail recursion. So again, evaluating, we want to make sure that we apply the transformation step on suspend, and we want a trampoline for stack safety. So let's revisit the functor transformers and talk about some of the interpreters that we can define for our to-do list. So we'll start with a test interpreter. This is a pretty common use case for free monads. So you'll create some trivial context, some id context, and have a method that will take your input and turn it into the new context. And this is where the cool stuff starts to happen. So our test interpreter is going to take some kind of mutable map, and in the interpretation, we're going to pattern match on that DSL, that abstract syntax tree that we created for our actions on a to-do list, and this is where the interpretation happens. This is where we say what it means to be a new task, to be a complete task. And here we're modifying the state, we're mutating the map, adding tasks, mutating whether or not they've been completed, building up that model so we can test against it. And then when we run it, this is what it's going to look like. We'll take our to-dos, feed it to our run-free function, and also give it a test interpreter. But we could feed any interpreter that we want there. And then we have the expected map that we can compare this against. And this is pretty useful for writing tests that would normally have side effects. But this test might shadow some business logic, and we're all good testers in here, so we don't want to do that. So let's write a different type of test interpreter, and this is going to be an action test interpreter. So instead of a mutable map, this is going to take a list of actions, and we're going to build upon that as we see them come across. So when we start to pattern match here, instead of mutating the state of the map, we're going to add the task to the end of the list that we expect to see. And when we run against this, our expected list will now test that the order of the methods and the order of the tasks that we see come in the correct order, and also that we see everything that we wanted to. And the useful thing, like I said, is because your production interpreters are probably going to be calling a database or doing something side effecty. And so the good thing about testing with free monads is you can define special interpreters that can bypass all of those side effects and test your expectations about the actions of the code without ever having to hit that or use any kind of testing mocks. We all know how much we love testing mocks, but if you could find a way not to use them, I bet some of you would. So a production interpreter might look something like this. Instead of transforming to that trivial id context, instead you're going to return an option. An option in Scala is either going to be a sum or a none, indicating that it either succeeded, maybe like a maybe type in Haskell, or that it didn't in some way. And so here, if your database write fails, you can return a none on this new task. And then this is why it's important that that return step is also a monad, because then when you're flat mapping, when you're doing that step, it will stop the execution. It will stop trying to do anything additional if the transform step fails. Revisiting some of the justifications, we talked about deferring side effects. And it's also useful for the multiple interpreters. Like I said, you're probably going to be talking to a database. We all need to talk to some kind of outside service at some point. Our programs can't be completely pure. So we need to enqueue messages, talk to a database, do some kind of HTTP request. And then you can also define the test interpreter that will suppress all of that and do the action test that we described or something like that. The other thing about free monads is that this is a solution that's pretty neat, but a lot of people introduce this into code bases because they can. They think it's a cool solution, but usually there is an easier way. So Jessica Kerr, program committee for this conference, gave this great talk last year where she talks about blue sky Scala. And she talks about the fact that there's the easy stuff in our programming languages, the green grass, the intro stuff, the hello world, and then there's outer space, the complicated stuff. The free monad isn't free because it falls into that outer space category, and the path to learning to get there is pretty broken. It's an impressive application, but not everybody understands it. You are all attending this talk, presumably because you wanted to learn something about this. So there's this good quote that I like from Marius Eriksson, who's a programmer at Twitter, that says, "Programming isn't math, and sometimes we hoist vocabulary that confers similar meanings." This is somewhat controversial, but I agree with him here. Some people think programmers need to be mathematicians and know category theory in order to be expert programmers, but not everybody does. Part of the reason we've been successful as an industry is because programmers are really good at adapting ideas and giving them to computers to execute them more efficiently. So our biggest skill is exactly this. We can do that. We can take programming languages, things like programming languages that are designed for humans. Otherwise, we would all still be writing bytecode or assembly. But we want good abstractions, abstractions that are going to make our lives easier, things that are going to make it easier for me to look at code I wrote 3 months ago or even 3 days ago and understand what I was trying to do. Jessica also talked about this in her talk earlier about Elm, how you want these good abstractions that make the maintenance of the code easy to understand. And I haven't even touched a lot of the magic that's happening behind the scenes here. So the reason that this is problematic is because there are a lot of abstractions out there that are more confusing than they're worth. Things like the free monad are mathematical concepts that have been applied in the programming domain, and they have some good abstractions, but for most of us, it's not necessary for our day-to-day work. So some of the reasons that you might want to avoid things like the free monad. Why isn't this necessary for everyone, and why should we avoid it? Well, I talked about that boilerplate, that DSL, the abstract syntax tree that we defined for a to-do list. That was 3 actions on a to-do list. If you think about your programs, what you would have to do in order to insert a free monad is make all of the implicit actions in your code explicit data types. And that's going to be a pretty big undertaking. And somebody told me that now Scala Z is doing this for you, but I still don't trust that you wouldn't have to touch that code. And it's easy to be frustrated with concepts like this, and it's not because they're necessarily difficult, but because a lot of times the learning curve, the path to get there, it's broken. That staircase is broken. Especially in the Scala community, people often assume that you should know this stuff, but the explanations that they send you to are based in category theory and assume a prior knowledge or a math PhD, or assume that you came from Haskell, which a lot of people don't. And that makes it hard to maintain this. It makes it hard to maintain projects like this. We want to stay in the blue sky. If you were in the space monad talk yesterday, that's, the outer space category. We can avoid that. The blue sky is for the 95% of us. So if we're not going to use the free monad, what are some of the alternatives available to us? Well, before we talk about that, I think it's important to mention that we should know the domain that we're in, know the domain that you're going to be programming in. Like everything in programming, this is going to be about trade-offs and totally dependent on your domain. So know your domain. This spectrum, very relevant for Scala, but also you can think about it in your programming languages and environments that you operate in. In Scala, you're going to get some code styles that come more from the Java side of things and some that come more from the Haskell side of things. So know the expertise on your team. A lot of my team came from Java, and so we try to make use of a functional style, but we're more likely to end up hiring ex-Java or ex-Ruby programmers than we are ex-Haskell programmers. So we're somewhat centered on this spectrum. So think about your languages. What is your language good at? Is it opinionated? You want to make sure that you're going to be able to maintain these projects. If you're doing something greenfield, ask yourself, are your coworkers going to be able to understand the abstractions you're using? Do you have the time and the tooling to make these worthwhile? And is this necessary for your business logic? All of these are trade-offs that you have to consider before you're going to introduce something like this. And that motivates how we think about things like maintaining stack safety. So if you're in a language or if you're in a code base that is using more object-oriented or imperative styles, then it's really easy for me to suggest that you just use a loop. But that can be hard if you're really invested in monadic constructs. If everything in your programs is already using monads, then it might be hard to introduce things that are simply looping. But as functional programmers, we need to keep in mind that sometimes the less functional style can be better. Especially in Scala, this is very true. If you look under the hood at the Scala standard library, everything is built using loops and mutable state and can build froms, and it's really ugly, and I don't know what this is doing, but it's good, it's a good abstraction. I don't have to think about this. This is nested away in the standard library, and I'm very grateful for it. So if anybody does know Scala, this is quite funny. There are also plenty of alternatives for managing stack safety, for maintaining stack safety. You can use plenty of other built-in monads, things like options or maybe in Haskell. You can error handle exceptions. Not all side effects are bad, though. Keep that in mind. Things like logging are really helpful. You don't necessarily want to suppress that. And in the free monad, if you're using the free monad in your programs, you're not going to be able to do any logging because you're not going to be able to do any of the side affecting stuff until the very end. And that can make debugging this stuff really, really hard. But we can look at an example of some code. So this, there was a talk a couple of years ago. A guy wrote a library that's a JDBC wrapper called Doobie that uses the free monad as the wrapper, in the wrapper for the JDBC library, wrapper around getting data out of databases. And so his argument was that there are too many problems with code like this. It's not safe. The result set operations on it can throw exceptions. You can't chain this. And that's all true, but using the free monad also isn't the only way to solve it. And that was his argument. So this is some code that I wrote for some of our applications, like 6 months ago. And keep in mind, error handling is good, but functional programming overlords aren't going to smite you if you decide to introduce a try except block. That's okay. I just want to remind you of that. So this code is just introducing some safety around our database polls. And for our purposes, this was enough. I think this took me like 10 minutes to write and get into production, and it was much more safe than what we had before. And for our code base, if there's a more functional way to write the code that's easy enough to introduce, I'm usually going to take that route. But again, it's all about the trade-offs that you want to make. I didn't want to introduce a free monad into this application because we don't touch it that often, and it's an internal API, and so it doesn't really matter if something unsafe happens every now and then. So keep in mind your domain. So if you want to look at this kind of stuff on your own, if you're interested in doing or experimenting with this, you're not going to have to write these yourself. You don't have to go and re-implement the free monad. Somebody has probably already done it for you in your language. Some languages have it built in. Haskell definitely does. A language like Scala has libraries that have done it for you. And I know most other languages, even non-functional languages, have ideas of some of the functional concepts that are available and exposed in different libraries. And we can look at a couple examples of things in Scala that I think are doing this kind of well. So for all my talk about Doobie, it does have pretty clean abstractions that are around the JDBC. It's pretty heavyweight. It's not something you're just going to introduce in an hour, but it does make things composable and more safe. And then there's a method called the task that you can use for concurrent programming. And this is an example from our code. And this is us queuing messages for SQS. It's a good abstraction for multi-threading. And I think this is pretty straightforward to understand, especially if you're familiar with Scala. It's a very clean abstraction. And I'm grateful for it because under the hood, it looks something like this. And I don't know, some of you might looking at code like this and trying to understand what it's doing, but I really don't want to have to think about this. This is too much for me to try to put in my head's mental model of how I'm working with a computer. But this is the kind of code that motivated this talk. This talk kind of came from a place of pessimism because we were seeing code like this in our production services, and we had to edit around code like this. And that's really, really frustrating when all you want to do is change the name of a JSON string. So what happened? What happened with my experiences? So the first company, the guy that suggested we just trampoline it, add a free monad. Shortly after he said that, he quit. But that was okay because he left the company. We never added a free monad. And it was a good thing because in that situation, the fact that we were seeing Stack Overflow errors was a really, really bad omen. We were writing an API for a very simple web service. There was nothing complicated about it. And the fact that we were seeing this means that we had grossly overcomplicated our business logic. So we did a little bit of refactoring. And even though it made our lives a little bit more complicated, it actually made things better in the long run. And then there was that data store application with all of the terrible code. But I eventually realized that even though it was using the free monad and I thought that was the problem, a lot of the problems with that application were unrelated. The thing about it is that application was really over-engineered. And it's really easy to do that when you start introducing concepts like this. You start thinking about these things, and they're kind of cool, and they're fun to play around with, and eventually you end up with a lot of tangled code that only the person that wrote it can understand. And the thing is as industry software engineers, most of us are getting paid by a company that's using us to make them money. And a lot of us don't have the large-scale problems that necessitate these kinds of abstractions. Again, know your domain. So after talking to a lot of people about the free monad, I'm still not convinced that it's the best solution, but I do see how introducing it in certain circumstances can make your code more composable and safe. I think the thing, if you take away nothing else from this talk, is that we just need to be judicious when we introduce abstractions like this. Just because we can doesn't mean we should. Sometimes it's okay to trade the most functional style for the sanity of your code and the sanity of your team. But if you're somebody that understands this well, we need to make sure that we're spreading that knowledge. If you're somebody that wants to introduce this in your team, make sure that you're willing to teach other people your ways and how to do this. The thing that we have to keep in mind is that you should assume people are competent, but you can't assume that they always have prior knowledge. You want to make sure that you're introducing these concepts using links and other things that will make this accessible. That doesn't mean we have to go overboard with those kinds of explanations, but we want to make sure that we keep this accessible to people. I used to think the free monad was pretty awful. I don't think that anymore. But if you're like me from a couple of years ago, and someone's proposing introducing this into your code base, I hope I've given you some tools to determine whether or not that's a good idea. Once again, I'm Kelley Robinson. Here's my contact information, and thank you for listening. Questions?
We got like 7 whole minutes, so we got to spend it somebody else's. There we go. You don't even have minutes.
What? Will you stop giving Elm the higher kind of type disrespect? Oh. Okay, well, having a park bench in the pub later. Dare I ask this? Yes, I dare. There seem to be 2 threads going through your talk. One, that the free monad technique used wisely is a very good one, used wisely, and I really enjoyed that. The other was, it seemed to me that Scala's quite fragile for these higher abstractions. Is that fair?
That is very fair. I originally wrote this talk for a Scala conference, and so it was very, very applicable for that domain. And I think Scala is one of those languages, like I showed with that spectrum. It's not opinionated, and you can do basically whatever you want with the language. And so you get a lot of camps of people that are on one side or the other, and so it's pretty divisive in that way. There's certain people that write Scala in a very, very functional Haskell way, and a lot of people that write it just basically using Scala libraries and APIs, but in a very Java OO way. So a lot of these problems are mostly relevant to Scala and my experiences there, but I think they can be applied to other domains.
Thank you.
Fairly simple one. Like, how long do you think it takes a person to really get to grips with this kind of approach of programming? Is it like a year or 2, or?
That's a good question. I think it depends on if you need to do this for your work, if you're looking at it in your spare time. I think it took me like a few months to grasp this, trying to develop this talk, honestly. I think there's definitely resources out there that are friendly, and if you start playing around with code, it also depends on your learning style. Like, I finally came to grips with this when I started actually playing around with code and seeing how it worked and making it compile on that kind of stuff. But it's not going to be like, if you're using this and these abstractions in like a production application and you've never dealt with it before, it's probably going to take some time. And I think that's basically the argument that I'm making, is even if like 2 or 3 people on the team are really familiar with this stuff and come from category theory or Haskell, as soon as you bring in someone more junior, even not someone junior, but that just comes from a diverse background than the rest of your team that came from Java or something like that, you're going to have a harder time integrating that person into the team. It's going to influence the hiring that you do for your team. And so if you want to only hire ex-Haskell people or people that are very invested in these kinds of paradigms, by all means, go for it. But I think the learning curve and that whole point that Jessica made with the blue sky is really applicable to what I was trying to achieve.
Cool. Taking that a little further, how is Java 8 and introduction of Lambdas changing the sort of Java developers that you've been introducing to Scala over the last few years?
That's a good question. Scala 2.12 was only like officially released yesterday, I think, which is the one that takes into account a lot of the Java 8 stuff. So I don't think I have a good answer for that yet, because
I meant more from suddenly you've got Java developers who are familiar with passing functions.
that's a good point. I don't know yet.
Can you repeat that last?
Oh, so the question was, now that Java 8 is introduced, which introduces things like Lambdas and other more functional style programs, does that help with the kind of learning curve? And it might help with like a lot of the blue sky Scala type of stuff that you're doing. Like even mapping is new to a lot of Scala developers that came from Java. That's not something that's necessarily, like you don't get that necessarily if you're coming from Java or Python or something like that. So those types of more, I guess I would call them straightforward functional styles might be easier, but I still think something like the free monad is going to be pretty brutal for someone coming from Java 8.
There's an old paper by Henry G. Baker called Cons Should Not Cons Its Arguments. You would find it very interesting.
Is that a question? Okay, thank you.
Do you think it's possible to sort of use these abstractions without having to learn them? Like the free monad, like understanding its deep structure and all that sort of stuff seems really powerful, but can it be used as a tool without knowing that deep structure?
Yeah, and I think that's on library developers to do that. So the thing that I mentioned about like task, that uses the free monad under the hood. I don't think anybody on our team knows that, except for maybe the people that watch, my coworkers that watch me give this talk. But I think it's up to library developers and us as programmers, if you're going to introduce that to do something, to make the APIs into that abstraction accessible.
Hi. As you mentioned, Scala provides the full spectrum from OO to pure functional. From your point of view, do you see that as a pro or con? For example, in a situation when you start with pure functional way and deadlines come on, and then you are starting to think, should I have some kind of escape hatches to maybe introduce some impure solution between the fully pure solution?
Yeah, it's more of a con in my mind. I think some people like it because it makes the language, in some ways it makes the language more accessible because people from different backgrounds can come into it and write in a style that they're familiar with, but it makes things very fragmented. So what was the second part of your question?
If you come into the point that you need to just
Oh yeah, so if you just need to deliver something. So I think that's on teams to decide how you want to build software. And I think this comes in, and not just Scala, but a lot of languages. If you want to trade, maintainability for getting something out the door, we all know how to hack together a solution that will get something to production tomorrow, but it might break a lot easier than if we took the time to design a system that's going to be more maintainable.
That's all we have time for.
Thank you.
Thank you, Kelley.